Okay. I would like to welcome our colleague Dr. Albertus Denny Handoko. Pak Albertus, apa kabar Pak?
Baik, Pak.
Baik Pak. Masih di Singapura Pak?
Masih, Pak.
Masih Pak ya. Terima kasih Pak sudah bergabung Pak.
Ya, ini belum mulai ya?
Iya Pak, jadi nunggu yang dari Oxford itu Pak.
Oh, oke.
Iya Pak. And then maybe I would like to say hello to Mr. Bartosz Mertas from Poland.
Hello.
Hello, Mr. Bartosz. Thank you for joining with us this afternoon.
Nice to be here.
Do you know where is Mr. Misal?
I don't know yet, but he should be soon.
Okay, thank you. So I hope you enjoy this online seminar.
Thank you.
Hello.
Hello, Dr. Misa.
Hello. Do you hear me?
Yes, of course. Your voice is clear.
Okay. I understand that the seminar begins. My seminar begins at 10 o'clock in my.
At
Not
Poland.
In Poland now we have 8 o'clock, and according to email, we start at 10 o'clock. Yes.
Actually, you will your session is 1 hour after this session. But if you don't mind, can you start your session, because I'm waiting the Dr. Enzo, but I don't know why he are not with us yet in the Zoom meeting. So if you don't mind, can you present your presentation, and then we will start with Dr. Enzo.
Okay, but I have some question. Can I start not at 8, because now we have 8 o'clock, and I need, in mail was stated that the presentation start at 10 o'clock in Poland time.
10 o'clock. So
I can I can send you an email, because I can start, but not at the moment. I can start that within 2 hours.
Okay.
Sorry, but I will send the email.
So yeah, because this is online seminar and we have a difference. We have a time difference. Sometimes there is a misunderstanding with the time.
Yes, but I had the time between 2 and 4 Jakarta time, and this is 10 between 10 and 10 and 11 in Poland. So
Okay, okay. So actually, according to Jakarta time, you will start at 3 p.m. Jakarta time. So it's
yes, yes.
1 hour ahead.
Excuse me, I will send the email with confirmation. I have received the email.
Yeah.
With the Jakarta time, yes, as you said, between 3 and 4 p.m. and this is between 10 and 11 in Zabrze. So have you received email from me?
Yes, yes.
Yeah, so it's between 10. It is a problem?
Yeah, actually, your session is not right now, but we are waiting Dr. Enzo, but I don't know why he he's
Okay.
not, with us.
If it is I understand that it is better to start session now, not at 10 o'clock. Yes, not at 3 o'clock in Jakarta time.
Yeah, yeah. If you don't mind, of course, but if you
Okay,
have,
so please let give me 10 minutes, okay?
Okay, thank you.
Because I need to prepare something, but you know, I was set at 10 o'clock, not at 8. So sorry.
I'm sorry.
It's a bit earlier because you know the set time of seminar was at 10 o'clock. So here we have 8.
Yes. So,
but okay, let's give me 10 minutes, okay?
Okay, it's okay. Thank you very much.
Okay.
Ya, saya mohon maaf Bapak Ibu, ada hambatan. Jadi seharusnya tepat jam 2 itu Dr. Enzo yang presentasi, tapi sampai saat ini belum join. Padahal sudah ada komunikasi dengan saya akan bergabung. Mudah-mudahan karena nggak kesalahan perbedaan waktu ya, gitu. Mudah-mudahan gitu. Tapi kita coba tunggu Mr. Misal kurang lebih 10 menit. Semoga Bapak Ibu mau bersabar. Terima kasih. So I just checked my email. So Dr. Enzo has already registered at this Zoom meeting. So I hope he will show up in a few minutes. Let's see. Okay, I see Dr. Enzo Liotti. Hello, Dr. Enzo. Hello, Dr. Enzo. Can you hear my voice?
This is probably because Dr. Enzo probably also have in mind to start at 9 o'clock.
So I'm sorry, maybe because maybe I forgot there is a time difference.
Yeah.
So welcome, Dr. Enzo Liotti.
Can you hear me now?
Yes, it's
Yeah. Okay. Yeah, that's good.
clear.
So is the can you repeat the time that it starts?
Actually, because you just show up, so
Yeah.
I asked Dr. Misal to start the presentation, but it's up to you, both of you, who will present first.
Right. Yeah.
Maybe Dr. Enzo or Dr. Misal, it's up to you. But we
if
are
there is
waiting.
possible, I prefer start after Dr. Enzo because.
Okay. So
yeah, it's fine with me. Yeah, start first is good. It's fine. Yeah.
Okay.
Yeah.
So we will start. So the first presenter is Dr. Enzo Liotti from Department of Materials, Oxford University. And as the head of department, I would like to thank you to Dr. Enzo that want to join with us this afternoon, Indonesian time, Jakarta time.
Yeah.
So please, you can start the presentation.
Yeah. One second. Yeah. Okay. Can I share my screen? Yeah.
Yes. I just want to remind you, you have 45 minutes.
Yes.
For the
Yeah.
and 15 minutes for the question and answer.
Yeah, no problem. Okay. So, do you see the presentation? Can you see the PowerPoint?
Yeah, I'm seeing it.
You cannot see it.
I can see it.
You can see it. Okay, then I can start. Yeah. So good. I think afternoon, everybody. My name I've been introduced already, but just a little bit of more introduction about me. My name is Enzo Liotti, and I'm a lecturer in advanced processing of material at the University of Oxford, the Department of Material. And I would like to thank you, first of all, the organizer for inviting me to this talk, which it was a pleasure. I'm in my presentation. Sorry? Okay. In my presentation, I'm gonna talk about the work we've been doing at Oxford using X-ray techniques to study metals, and in particular metal processing and the solidification of metal alloys. So carry on. I'm gonna give you a bit of introduction of my background and the project, and also speak a bit about why we study solidification and why using X-ray to do X-ray imaging to do that. Then I'm going to move on and speak about the kind of experimental setup that we have developed to carry on these studies, and give you two case study of the work we do, and they're both on grain refinement of aluminium. One is the first one would be on what we call intrinsic fermentation, intrinsic grain refinement, which is dendrite fermentation, and the second one would be about extrinsic grain refinement, when you add actually seeds or little kind of like a nuclei to the liquid to get like enhanced crystal nucleation. So the work I'm presenting has been done in collaboration with many people, and the main co-author are Professor Patrick Grant, Andrew Liu, and Robin Vincent in my own department. Carlos Ateta and Professor Andrew Zisserman at Oxford Engineering in the computer vision group. Professor Lars Hartmann and Professor Ragnvald Mathiesen at NTNU, which is a university in Norway, which is one of the in Europe. And then Thomas Connolly, Igor Dolbny, and Michael Hart at Diamond Light Source, which is the UK Synchrotron facilities. Professor Zipeng Guo and CB at Tsinghua University in China, and Sundaram Kumar, who works for Novelis now and was at the time of the experiment like a collaborator here in Oxford. The work is part of a larger project, a UK larger project, which involved 5 universities, and the topic is liquid metal engineering. And this project, which is the one we've been used for funding in the last kind of like since 2011, also include many other companies, some nationals and some other international, like Constellium, for example, or SAPA. And also we have been kind of collaborating with several institutions, such as like Synchrotron.
I'm sorry, Dr. Enzo, I interrupted. On my computer, it's not the full screen of the slide.
Okay. Give me a second then, yeah. Is it now full screen?
Not yet. Not yet.
Maybe you can try to press F5, Doctor.
Yeah, yeah. What about now?
Yeah, it's okay now.
Yeah, okay. Yeah. So why do we study solidification? Well, if you look around you, solidification is it's, you know, any component or any items you see around you probably include at least one casting that has been produced has gone through the solidification step. In fact, 90% of the manufacturing goods contain at least one casting, right? And also, if we look at the metal processing chain, we can see that solidification is generally almost every time the first step of any component, and therefore the microstructure you obtain at the beginning will have a severe influence on the mechanical property of the final product. So it's very important to get this right and correctly. The third reason why we study solidification is that because if we look at the emission worldwide, we can see the metal industry is responsible for 8% of the greenhouse gas emission. And to reduce this emission has been found that we have to increase recyclability. And this is quite interesting for metal alloy, because recycling aluminiums save 90% of the energy. That's not a very big news. And also 75% of the aluminium around is still kind of in circulation. However, every time you go through the recycling cycle, the quality of the material you are recycling decrease. And therefore, still nowadays, industry dilute secondary alloys with primary addition to basically bring back the quality of the material to an acceptable standard. And this has all the disadvantages of needing to actually have to extract primary material to basically produce like enough quality. So that's not a demand problem. So, and the second possibility is to enhance performance. Both of these kind of criteria are heavily dependent on solidification. If you get a material with a very good microstructure with a lower level of defect at the beginning, then you will have better performance. And if you can control solidification wisely, you can probably reduce the needs of like diluting the alloy. So my research is focused on understanding the fundamental phenomena that take place during metal processing, to then trying to enhance the quality of the material produced by metal processing, and also learn how to control the microstructure to manipulate them to the needed requirement. So I see my work like set like in developing technique that allow to do that, to then study solidification and improve manufacturing. So X-rays are very powerful tools for material scientists, especially for metallurgists. If we use a synchrotron, we can use X-rays to study the structure. If we study the material ex situ is when you study the material at the final product. So for example, you do a casting and then you cross-section and you're looking at the microstructure with the microscopes. That's an ex situ experiment. So you do it after, right? You're doing. When you're doing situ experiment, essentially is when you're looking, for example, a process while it's happening. So that's allow you to catch the dynamic of the process, which is very important, especially in very dynamic phenomena such as solidification. So traditionally, metallurgy has been studied by post-mortem approaches. So the typical case is what I just said, like you take a sample, you cross-section, and you look in with an optical or an SEM, and you see the microstructure. However, it doesn't actually tell you the entire story, because the microstructure you attain in dynamic processes are often the results of the process itself. So actually looking only at the final stage, it might not tell you the entire story. Therefore, using ex situ imaging is using like modern, like third generation synchrotron, which are quite widespread nowadays in pretty much all the continent, allow you to see the dynamic. And by seeing the dynamic of solidification, you can learn about the nucleation and growth of the various phases of the solid to solid interaction, and etc., etc. It gives you really a lot of information. So how a normal radiography setup works? Well, normally you've got a sample that we use a very thin foil encapsulated in a container. In this case, is a quartz like cell, and then we put it in a furnace, which is a small Bridgman furnace. A Bridgman furnace is a furnace that has two chambers, and they can be controlled independently. In this case, you see a heater on the top and a heater on the bottom here, and they can be controlled independently. And because they can be controlled independently, then we can impose an isothermal condition, or we can impose like a thermal gradient and then cool a different cooling rate. And by putting the sample in the middle, like you can see here, then you can see like you can control the solidification. Furthermore, our rig allowed to put like a little electromagnetic steerer that allowed to move the liquid in the sample while you are actually imaging the formation of the dendrites or the solid. And that's actually done by putting a little like a small ring magnet and actually connecting two wires into the sample from the bottom to the top. And by passing a current into the sample with the presence of a magnetic field through the sample, you can actually apply a Lorentz force, which is controlled by the type of electrical pulse you put in. And then, as I said, you pass X-ray through your sample between the gaps between the two heaters, and then you can collect the transmitted signal with an optical system at the synchrotron that then give you an image, and an image that look like this one. Right. Okay, like a few more details about the setup. This is a detailed kind of image of the sample. You can see the two wire here on the left, and then you can see the sample is covered by a coating. Normally it's boron nitride spray powder, just to avoid that the contact with the silicon of the quartz will basically dissolve the cell. And as you can see here is an example of how this little setup works. As I said, the B is the magnetic field that passes through the sample. I is the current that can be controlled because we use a pulse generator, so you can put like different kind of pulse in it. And then the yellow is the Lorentz force. So in this case, if the magnetic field passes in the plane of the sample, so it's perpendicular to us, it's coming out from the screen, and the current goes up and down in this direction, then the Lorentz force will be the other direction. These are a few examples of the rig set as during an experiment. In this case, the experiment was done horizontally, and these were as a thermal study, and this is a setup at the synchrotron. So, as I said, like the example I'm going to speak about are grain refinement. So, a typical casting as a coarse, columnar, anisotropic microstructure, we retain normally high microsegregation. That's what happens if you try to cast a component and you don't do anything. Just if you pour the liquid in the metal, the columnar microstructure tend to be favored. What you really want to obtain naturally is a grain refined microstructure. So an equiax fine anisotropic microstructure. We retain little microsegregation and that look like this. So like this is a macro scale, and this is actually the small dendrite, right? So to grain refine an alloy, you can use an intrinsic method where you, such as grain fragmentation. And intrinsic is because you are not adding anything to the material, but you are essentially use external field or to continuously disrupt the growth of the columnar dendritic array. And that the disruption and the breaking of these arms will generate new crystal as they grow and grain refine the material. The extrinsic instead is when you add micron-sized particle to the melt to promote nucleation. A typical case in aluminum is the addition of TiO2. The first example would be regarding intrinsic grain refinement. So if you think about this method is already in place, for example, in continuous casting, where there are several along the curve, there are several electromagnetic steerers, like one normally 2 or 3 here. And what happens if we look in detail, we can see that essentially the electromagnetic steerer, which by the way, the primary goal is to homogenize the liquid and avoid or diminish microsegregation. But also the steering lead to the fragmentation and the breaking of the dendrite arm, promoting like an equiax microstructure. This is an example of the effect of adding a magnetic steering to an iron to a still sample, and you can see with and without the PMF in different conditions. So it is known that if you stir the sample, you enhance the formation of an equiax microstructure, but what is the mechanism and can be optimized? And then what is the role of the fluid flow? So it's just like mechanical braking, or is there another mechanism? And can we exploit it more? So with our little rig, which I showed before, we could essentially have several different setups. So because we can control the temperature of the two heater, we can do the solidification from the bottom to top, top to bottom. And also, by putting the wire in different location, we can steer the liquid in different way. So if we put the wire at the top and at the bottom, then we steer the liquid horizontally compared to the grow direction of the dendrites. Otherwise, we can put the wire on the left and on the right and actually steer vertically, right? And also we can tilt the rig. And also the pulse can be oscillatory, can be like a sinusoid, square, or triangle, but can also be monodirectional. So like always positive, always negative pulse, and again with different shape. So there is kind of, it's a very small setup that allows to test many conditions, right? So the one I'm showing first is the example of like a monodirectional, continuous, and a sinusoidal oscillatory case. So the type of experiment we were doing, which we call fragmentation experiment, we had this kind of setup, and we were cooling, imposing a thermal temperature gradient in the liquid. So the material starts as liquid, then we cool to a constant cooling rate, and both the heater cool at the same temperature until the dendrites were growing in the middle of the field of view, as you can see here. And then at some point, when everything is kind of steady, we switch on the electromagnetic steerer. So what you see here is an example of the growth of like a columnar dendrite, where there is a continuous, a continuous kind of electromagnetic field. So you see the dendrite growing, right? At some point, the PMF is still off, and at some point will be turned on, and you will see that essentially this is actually pushing this direction, and you see it's remelting this direction, and here is remelting here, right? And this actually, in this case, because it's continuous, it's almost a steady state. The interesting thing is that you are remelting the top, but if you look carefully inside the mash zone, not much happens. So this condition, in essence, doesn't really lead to fragmentation. It just leads to a kind of like steady state flow that make the liquid to recirculate and remelt the material. This case instead is an oscillatory case. So what happened is the dendrites are growing, and here we are actually using a sine wave of 1 Hertz, which is positive and negative. So the liquid is steered left and right, and the dendritic array is growing. And if we go at time around 30 seconds, right, the PMF will be turned on, and you will start to see like fragmentation taking place. It's about 32 seconds. This was grow like is an aluminum copper alloy, and you can see, if you look carefully, we are steering the liquid. Clearly, you don't see very well the liquid steering because you can't really see the flow, but you see the effect. So you see that there is a lot of secondary arms that are breaking. And of course, in this case, because it's static, they just are basically stuck in the mash zone. But equally, they are breaking. So you can see, and if we speed it up this process, and I'll do it. So you can see when like this, and they're moving with the flow. So it's a sinusoidal wave of 1 Hertz. So we are moving and steering the liquid on purpose. And you can see that it's taking primary, secondary arm, tertiary arm is breaking anything. And remember that in the mash zone, you got the liquid, and we are steering that liquid as well. So we are here, and I speed it up so it's a bit more frequent. You can see that it's very noticeable, and you've got a lot of this breaking. So we carried out a lot of experiments more than 300 solidification experiment like the one we have shown you, with different kind of like setup, like bottom to top, with and without the EMF, top to bottom, and then like one with a vertical steering, and even horizontal solidification. But in the presentation of today, I'm focusing on the first four, so the bottom to top and the top to bottom case, with and without the presence of steering or electromagnetic steering. So this is an example of the difference of the grow direction. So these are two arrays which are equivalent in everything apart from the direction. So when the PMF starts, you can see that at some point there are, when you see the yellow, there is actually a braking, right? And normally braking doesn't take place immediately. It takes always a bit of time, about a few tenths of seconds. And you will see that the bottom, when they start to basically fragment, is normally, there is more fragmentation in the bottom to top than in the top to bottom. And if you can notice, actually, the top to bottom are almost oscillating with the flow. So there is a sine wave of 1 Hertz, as you see, and these dendrites are actually like if they were tree in the wind. Again, I'll speed it up a bit so it's a bit more clearer. You see that the fragmentation is incrementing. And if I go fast, you can see there is a lot of happening in the bottom to top, so the video in the right, and not very much in the other one. Right. So what happened is this is actually the final count. So if divided in time step of 30 seconds, right? And there was like this is on the left here you find two videos that is the top to bottom and the bottom to top. And that's actually as time passed. Right, so you should look at it horizontally like that. And you can see that the case at the bottom to top is significantly higher than the other case. In fact, the other interesting thing is that the distribution of breaking event is the information we could learn about this, and the fragmentation rate against the processing parameter. And what we were trying to achieve and to understand is the fragmentation mechanism. So by analyzing 39 video sequences and counting pretty much 8,000 fragmentation events, we were able to find, to basically produce this curve. This curve are basic fragmentation rate curve as a function of time for the various cases. So there are basically two reference cases for the bottom to top. So the bottom to top where we're not doing anything, not steering, so it's actually the green bits. The red one, which is the bottom to top when we were steering, and then the same for the top to bottom. And we use two different kind of like strength of the magnetic field, so like more force, right? If we compare the top to bottom with the bottom to top, and this graph here, the A, show you the ratio of the fragmentation rate of all the top to bottom compared to the bottom to top, we see that essentially solidifying the material with the grow from the bottom to top were always favored. The fragmentation rate was higher at any time during the experiment. While equally, every time we use a magnetic field, we obtain more fragmentation than without it. So the bottom to top is always higher than the top to bottom, and so it was when the electromagnetic steering was present compared to the case without. The other thing that was interesting is the distribution of the fragment within the Mashi zone. Somebody would expect that the most of the fragmentation take place at the tip, within the tip region. Actually, we found that there was almost a log normal distribution in all the experiment, but show that fragmentation take place more or less to a depth of a few hundred micron in. That's the peak is always the same, and that is independent from the top to bottom or bottom to top. So that tells us something about the mechanism. Also, we started to look at the inside the Mashi zone, how the distribution of the solid gradient is. So If the mass zone is like this, the one at the image in the center, the solid fraction is 0 at the top and then will increase going down, right? And we measure the solid gradient. So by looking at the images in the liquid and measuring a lot of the concentration of the liquid within the interdendritic channel, we were able to measure the solid gradient as expected. The solid increase by increasing the solid fraction, but also this horizontal gradient, which is actually represented by this like a color map, increase while you go deeper in the mass zone, as shown here. These are actually individual measurement of the solid gradient in the horizontal direction as a function of the depth in the mass zone. And here show like a fragmentation of a primary dendrite, and you can see that the gradient was very high in the area, local area nearby the breaking. So what this is telling us, well, when we started to look at and compare the fragmentation rate with the solid gradient, we found a correlation. So essentially, this is important to understand the mechanism. So the higher is the solid gradient within the liquid, the higher is the fragmentation rate. And the explanation, we look in this kind of mechanism. So you need three fundamental key aspects to obtain, to fragment like a dendritic array. The first one is that you need a solid gradient. So if you are in an interdendritic channel, and this is a schematic of a primary and secondary arm, you've got some vulnerable region, which are region of high curvature, which are essentially the neck of the secondary dendrite where they are attached, and also primary kind of like thinner area. And also you got a solid gradient in the channel. So if the solid gradient would be essentially, if the concentration of the solid would be flat, then even if you destabilize, if you move the liquid, there would nothing really happen. If you got like a little bit of concentration gradient, then the effect in destabilizing this vulnerable region will decrease. But if you got a steep concentration gradient, then the effect of a destabilization force, that could be our electromagnetic steering, is increased, and therefore you got more chances to break out this vulnerable region. So to summarize, what you need to enhance fragmentation is a grow condition that favor the formation of this vulnerable region, so that favor the formation of high curvature area. And also you need like an alloy that is a destabilization force, and you need actually quite steep solid gradient within the mass zone. The second case, study case I'm showing is the one of extrinsic grain refinement, and is regarding inoculation. So the use of like of TiB2, especially in the aluminum industry, is widely applied, but it's not very widespread for other metals. There is no many grain refiner for steel or for like cast iron, for example, right? And also the efficiency of the inoculation is very low. Of the TiB2 particle you put in an aluminum alloy, probably only 1% of the seeds nucleate. The rest is inactive. So also it doesn't work for intermetallic phases. There is not yet like a grain refiner for the intermetallics in aluminum alloy, for example, in the 2000 or 7000 series. So here is an example of nucleation of aluminum alloy from the liquid. What I'm going to show you is three video sequences of the solidification of an aluminum 20% copper, which was grain refined with TiB2. And the difference in the three video is just the cooling rate. So from the left is 0.3, and the one on the right goes up to 1.5 degrees a second, right? And these were solidified near isothermally with the two heater kept at the same temperature and grow horizontally. So you can see that the grain forms, and the one on the right is faster, so that they appear in the field of view much faster. And but also qualitatively, you can see the solid segregation. So in the mass zone, the darker color, darker blue, compared to the bulk liquid. But one thing that immediately visible is that despite the fact that it takes less on the right side to solidify, that's just for pure like for cooling rate, you can see that the nucleation was more copious. And in fact, if we go towards the end of the video, which is somehow here, you can see that the grain size, even by eye, without any measurement, it's much higher, like on the right than on the left. And that's kind of known. If you increase the cooling rate, you increase the nucleation rate, you get a smaller grain size. So that's so far so good. Now, this other example is the effect of when we stir it. In this particular case, we took an aluminium 25% alloy, grain refined with TAB2, but cooled very slow at 0.1 degree a second. Again, still in near isothermal condition. And what I'm showing here is the example without a PMF, so without stirring and with some stirring. And the stirring here was done at 0.1 hertz. So this is actually the video speeded up for convenience, so it's going very fast. And we can see that actually, you know, the dendrites are shaking and are appearing in the field of view and going. But apart from the you know, the nice fluctuation of the dendrites, one evident case is that this stirring is increasing the nucleation rate. If you look carefully, even without counting, you can see there are more grains forming here than here. And the second effect, they impinge on the growing dendrites, effectively blocking the growth of the columnar grain. You can call it a sort of induced CET, right? And if you look on the left, in fact, there is not much nucleation and the dendrite are happily growing like basically columnar structure. So that's an example. Bear in mind that the PMF is not always effective. It depends how it's applied. So in a complex casting, this situation will be much more chaotic. So again, we've done many of these experiments. We spent 55 days at the Synchrotron, you know, using different synchrotron here in Europe, in Switzerland, in the UK, and in France. And we managed to collect 1,400 experiments with all on aluminum copper with different solid content, with and without the grain refiner, with and without stirring. And we cover a wide range of certification in essence. And that's accounting for more than 50 terabytes of data, which is more than 10 million images, right? So most of these experiments were of very good high quality, like the video, like the image you see on the left. So you could actually get a lot of information out of it if you could analyze it. So the first thing is, like, by counting the grain, you could estimate the formation rate and learn about the, you know, the efficacy or the potency of particles of grain refiner. You could quantify the growth rate if you could measure it, measure the elemental field in the liquid, because the experiment allowed to get like a concentration of the solid in the liquid phase, and also get information about fluid and grain flow if you can track the grain. And if you could got all this information, we could compare them with nucleation and growth theory and test their validity, and also do that as a function of all the solidification parameters. However, if we have to do by hand, even just the counting would imply that we have to basically pass our days putting dots on a screen, because essentially a typical experiment has maybe 200 or 300 frames that are the usable kind of useful kind of range in which you start to see grain until the solidification is finished. And that means that if I want the nucleation rate, I should go in each frame and count, right, the grain, so put in dots. And that has to be done by 1,000 experiments by 1,000 frames. So that would be still feasible, probably very time consuming, but very kind of unrealistic. However, information about the growth rate, we could maybe measure manually the growth of one single grain or so. But if we want to gather statistic and get the full power, extract the full kind of like information, we need to do that for all the grains, and that became like unfeasible. Therefore, we work with the computer vision group in engineering to develop a machine learning algorithm that were able to understand the images. So we trained 6 video out of 140 of the one we analyzed, and the algorithm were then capable of recognizing the grain and in a new unseen video. And then we use that kind of detection algorithm to attach like basically a measurement algorithm. So once the grain were detected, then there was another part of the algorithm that was measuring automatically the grain size, the formation rate, grain growth, nucleation under cooling, diffusion length, grain movement and more. So here is an example of the algorithm at work. So you can see the dendrites are growing and it's detecting the velocity. So you can actually have a movement and velocity. And also it's detecting the grain as they form and is tracking their growth. And this was done so far for 140 of the experiment that we done out of 1,000 and something. So you can see that they rotate and they go. By measuring, as I said, 128 video sequences, we were able to detect 14,000 separate nucleation events. So each of them correspond to an individual dendrite, an individual equiax grain. And that's actually, we're summarizing in terms of formation rate as a function of the cooling rate. So of course, the curve became more intense, but also you can see that there are interesting correlation when you start to change the alloy. So increasing the cooling rate always increase the formation rate. That's just because of the evolution of the solid fraction is faster, but also it was more effective when there was more solid. So for example, the increase in the cooling rate, it's more effective in the aluminium 25 copper compared to the aluminium 10 copper. And that's actually seen here as well in this figure in B, where you can see that essentially the effect of the cooling rate was much more effective at high solid content compared to kind of like low solid content. Another interesting aspect that was actually found with by analyzing all these data, and I was always theorized, is that enucleation in a temperature gradient doesn't take place as a continuous, but they actually come in burst. And as you can see here, this is a graph, a live graph of the formation rate of the crystal. And you can see within the video, there were essentially 3 big waves. So nucleation is not continuous, but it's kind of almost recharging now, and then will be a final wave that is taking place now. So, right. And so this was crucial to understand the way in which nucleation takes place and how maybe it could be controlled. In fact, by looking at the video, we were able to correlate the frequency and the intensity of these waves to the concentration of the solute. So when we have more solute, essentially we've got these bursts are essentially more frequent, so they take place at a higher frequency and they are more intense. So the effect of solute, essentially, when you don't have, like when you got a low content solute, nucleation is almost quite like a continuous, in the sense that it happens very infrequently and very slowly. While the more solute you put, you favor the formation of a solid suppressed zone, and therefore when nucleation takes place, it happened in the form of a wave, of a burst. And this was explained by looking at the effect of solid suppression. So the solid suppression is a concept that showed that by increasing the solid content, essentially you increase the size of the solid suppressed zone. So the solid suppressed zone is that takes place because there is partitioning. So when you got a solid forming, right, it will segregate. In the case of aluminum for hypothetical alloy, will segregate solute into the liquid. In the case of an hypereutectic alloy, it would be the same. Will actually deplete the liquid of solute. And if you create the blue area, is a zone in which nucleation cannot take place because it's been suppressed by the presence of the solute that been rejected by the solid crystal. If this area compared to the overall undercooled area is large, then when nucleation take place, essentially, it will take place at higher undercooling. And the schematic here is show that essentially what happened is you are able to activate more grain when you solid suppress more, because essentially you suppress the easy to nucleate grain that will basically kill the nucleation of higher undercooled seeds. With this, I conclude like my talk. So the take of the talk is that X-ray imaging can give you the dynamic of the phenomena, which is a key point to understand the fundamental phenomena taking place during solidification, for example, or any other processing phenomena which is dynamic. It has become like almost an indispensable tool for the study of solidification phenomena, as demonstrated by the number of increase, the increase of number of studies of this type published in the literature. And that's also because the number of synchrotrons that offer an imaging beamline is increasing. So there are more people who have access to these tools. These techniques have been capable of giving new insight in science, especially new kind of like type of data that were not available otherwise. So the bursts of solidification were hypothesized and like in the early 2000s, but this was the first direct like evidence that they existed and of these bursts. The interesting thing is that now it's relatively straightforward to do this experiment, but it needs automated analysis to be fully exploited, and especially machine learning, because of the sheer number of the size of the data set you create. It's unthinkable to approach them manually by manual analysis. And also, it is very important to work on the repeatability and robustness of the data analysis. So often there are like groups, often there's like, you know, if you cannot do automatically, you ended up analyzing maybe 1 or 2 individual experiments out of a data set of 100, and you don't get out the full information that you could extract from the data. And with this, I conclude my talk, and I leave you with this funny video of the dendrite. So thank you very much for your listening. Please, I'm here for questions.
Okay, thank you very much, Dr. Enzo. So, if the participant want to ask 1 or 2 questions or more to Dr. Enzo, please, you can unmute your microphone and you can ask directly to Dr. Enzo.
First, okay, sir.
Okay.
Yeah.
Please.
Okay, thank you very much. Interesting talk, Dr. Enzo.
Yeah, thank you.
Yeah, I'm wonder about the deformations of you put 2 metal and make a alloy. And is there available and is there capable to distinguish the deformations of the solid states of the metal, the alloy that you create? The first question. And another question is, can we use oxide material to distinguish the oxygen content in our sample? I mean, your sample is alloy. How about the metal oxide? Is it available to use your method to distinguish the oxidation state of the compositions? Thank you very much.
Yeah, can you repeat the first question, please?
Yeah, the first question about the deformations, the crack deformations of the sample. Yeah.
Okay, so the question is, yes, the sample, think about, is like, it's basically a 200 micron thin sample, which when it's solidified will shrink. So it's like literally a bag, a plastic bag when it shrink, right? So because we are looking at the plane we're looking through the sample, that doesn't really matter for our type of imaging. So we were looking basically a sample of more or less 25 by 15 millimeter in size, 200 micron thick. But the area we were imaging, it was normally 2 by 2 millimeter in the center. So there are other groups that are work with deformation. So you look at the deformation, for example, of the Mashi zone or things like that. But that was not our interest. So the answer is you could use it for it, but we didn't do it. The second answer is regarding oxide. The images in these videos are created with what is called absorption contrast. So essentially the X-ray passed through the sample, and X-ray has absorbed a different rate for different elements. Therefore, in this specific case, aluminum is more transparent than copper, right, to the X-ray. So you can distinguish segregation of the solid element if you got a binary alloy. So example, we use aluminum copper, wherever is darker or brighter, essentially you got more or less copper. If the oxide will have a different composition than the metal, in particular in terms of density, then you will be able to detect it. The fact is that in our sample, for example, there is always a film forming on the surface, right? That's generally is too thin to be detected. So if you've got a 200 micron thick sample and your layer is 1 micron, then there is not really a chance that you can distinguish it. But we had experiment which you use another type of contrast. We were able to basically look at the surface, so you can detect it. In terms of inclusion, if you got particle or you know, like intermetallics, then you will see them. Yeah.
Thank you, doctor.
Yeah, no problem.
So please, the next question from the participant. Maybe the Dr. Enzo, I want ask
Yeah.
you a question. So,
Yeah.
my understanding that the setup is like it's not you know the casting mold is maybe it's just a flat surface, and then you put the the aluminum and copper on the top of the surface, and then you hit the sample. That's the setting of the experiment. So it's I mean the thickness of the fluid is not comparable to the let's say on the continuous casting and the industry.
No, you're right. So the alloy was basically, we prepare a small bulk sample of the alloy, and then we slice and polish thin slices. So the alloy is pre-made before. You're right, the flow in these conditions, you can simulate, let's say, some ideal state. So when you go like flow in one direction or another, so you can, it's semi 3D in the sense that you don't have the third dimension because of the thickness. If you want that, you should go to tomography, so it's 3D. The problem of tomography is much more complicated to analyze the data and to carry on the experiment because you don't have a live view of the image, so you cannot see what happened in your sample when you're doing the experiment. But what we could reproduce here is some kind of case scenario. So for example, because we could control the steering very accurately, so the strength and the direction, then we can replicate certain scenario. So this is let's say is like you can do model experiment and learn from that the effect. It's very difficult to replicate a proper casting condition, but we did some experiment where we were steering in we call it a vortex, right? So by putting multiple wire and shooting them like sequentially, you can create a very chaotic situation, which is the one of a casting, for example. The problem then is that what you learn from that, because your experiment is so complicated that then it's very difficult to learn any meaningful data.
So maybe the type of the flow, it's like laminar flow, if I'm not wrong.
It is laminar, quite likely, yes. You would see what happened in the Mashi zone. So you know, you're not gonna replicate what happened in the flow when you cast, for example, in the filling system, right? But you could replicate what happened, for example, in a filter. So I haven't shown, but we did some experiment in which you can see the material, the liquid. So if you add a little bit of lead to your aluminum alloy, the lead will form a monotectic reaction. That means that the lead will basically form liquid droplet within the liquid aluminum. And we have used that to basically start to measure the flow in the interdendritic region, right? So you can get information about the fluid flow in the Mashi zone at high solid fraction. What you would be difficult to do is basically just replicate the flow of a filling system. So if you've got a normal casting, sand casting, that is probably still better than with other methods. Also because the scale of our imaging is quite small, so it would be a very local measurement.
And in the setup of the experiment,
Yeah,
the substrate is it's similar with the, let's say, the material of the mold, in the continuous casting, or
no, the material, the mold, the case of the sample, like in this case was a quartz, or we use boron nitride, or any other material that is X-ray transparent and is easy to handle. So the capsule is there because if you don't do it, the sample is basically floppy, it won't stay. If you put a vertical thing, it will just basically fall down, right? What we try to do, for example, when we use quartz, we cover the sample with boron nitride powder to avoid that the aluminum will react with the silicon, because if there is quartz, you got silicon in it. If you just carry on the experiment, essentially you are dissolving the silicon in your alloy. But no, we're not using the same material of the continuous casting like mold.
okay. So, is there any question from the participant?
Yeah, hi.
Okay. Oh yeah, Dr. Albertus, please.
Hi, Professor Enzo. I'm Albertus. I'm from ASTA IMRE, Institute of Materials Research and Engineering.
Yeah.
It's a very nice, interesting talk. I personally have not been involved in the solidification work, but I'm working in the phase engineered materials.
Yeah.
My question is this kind of technique can be applicable to differentiate phase? Like we also use thermal to change the phase of materials to control the phase, but not to the point that when they solidify. Is this X-ray radiography work can be applied to this kind of work?
Yeah, in theory, yes, you could apply. I mean, we use it to let's say to image the liquid to solid transformation, solidification. But you can use it for any dynamic phenomena. So if you're interested in phase transformation in the solid state, you can do that as well. The point has to be designed for a specific case. So, I mean, you can get the contrast a different way. So that has to be tailored to the specific application. So I'll give you an example. If you want to image a phase transformation of a phase that is just changing crystal structure, but not much composition, then the kind of setup we use, it won't distinguish it. But you could use diffraction. So you could use another type of setup that will give you that kind of information. Or you can use detector that give you the composition of a multi-elemental material, right? So you could map more than one element, you know. We, for convenience, use binary alloy because they are easy to study and you can learn the science behind it. But nobody stops you to do look at ternary alloy or a different problem. The key point of imaging is that it gives you the dynamic. So if you are looking at phase transformation, that would be interesting, yeah.
Okay, thank you. And another follow-up question is that because I think access to centralized facilities in this region is actually quite limited.
Yeah.
So do you think that these kind of techniques can be done on lab scale X-rays or?
Yes, I mean, so first of all, I would say in the last 10 years, the quality of lab scale machine has improved a lot. And now there are groups that manage to do not everything, but certain kind of experiment on a lab machine. So you can do the only thing you need to do is build like a little rig for your specific application. So a little furnace or something that fits your machine. Secondly, a lot of this work is done in collaboration. So we are always open to work with other people. We work with people in Australia. We work with people in Japan. Or in the States. So there is access facility for this, for Synchrotron is worldwide tend to be kind of you write a proposal and then you generally the time is granted on the quality of the proposal. So if you think about anything, it can be done in collaboration with me or any other group that do these sort of things.
Okay, right. Thank you.
Yeah. No problem.
Thank you very much, Dr. Albertus. So, do we still have a question from the participant? Okay, so I think we don't have any question for Dr. Enzo. Before we close this first session, I want to ask Dr. Enzo, do you know Mika Filipa from Portugal?
No, I never met him. Yeah, nice to meet you. Yeah.
Okay. So because I check your Facebook and you are friend with Mika Filipa from Aveiro, Portugal.
Oh yeah. Yes, I know her. Yeah.
She's my friend because I got my master degree at Aveiro University.
Really? The
Yeah.
world is very small. Yeah, Mika used to be my housemate for a long time
Okay. So
in Oxford. That's very small world.
yeah.
I will. Yeah, that's very interesting. Yeah.
Okay. So thank you very much, Dr. Enzo. And
Yeah.
I hope we will meet again.
Yeah. Hopefully. Thank you very much for the invitation. I really enjoyed to give the
Okay.
talk.
So if you don't mind, we hope you send your presentation by email.
Yeah.
Because I will send the slide to the participants today.
Yeah, the recorded video. Yeah.
Mm-mm.
Yeah. Okay. Yeah, that's fine. Yeah.
Okay. So Dr. Enzo, thank you very much.
Yeah. Thank you very much. It was a pleasure.
Bye.
Bye.
So we have completed the first session. The next session, I will present Dr. Michal Resdak from Poland. Dr. Michal.
Hello, I hear you very well.
Okay.
You hear me now, or do you see me?
So
Okay.
the screen is yours, Dr. Michal.
Okay, I will try to share the screen. Do you see my presentation?
It's okay now.
It's okay now. Okay. So, hello once again. Good afternoon, ladies and gentlemen. First of all, I would like to thank Sultan Agent Tirtoyasa University for possibility of make presentation. My name is Michal Rajdak, and I am an employee of Institute for Chemical Processing of Coal. Our headquarters is located in Zabrze, in Silesia district of Poland. We are research institute focused on development of technology related to coke making, hidden power production, and waste processing. Today, I have a pleasure of giving a lecture entitled Cokemaking Technologies, in which I'll try to present matters related to technology of coke production, which is an important raw material for the development of world economy. There is agenda for presentation. In general, I try in brief way to approach the process of coke production. What is coke? In general, coke is a porous material containing an organic and inorganic part. The organic part is mainly elemental carbon and also hydrogen, oxygen, and small amount of sulfur and nitrogen. Generally, coke is produced by carbonization of coking coals in coke oven batteries. What is coking coal? The coking coal is some kind of coals. It's bituminous coal with an average qualification degree, and the characteristic feature of which is that it passes through a plastic state during its heating without air access. It's called pyrolysis process. And passing the coal through the plastic state, this occur at about between 350 and 500 Celsius degree, enables the formation of coke, texture and structure. Above this temperature, in general, resolidification and further devolatilization takes place. There are generally three main types of coke produced: blast furnace coke, the production of which accounts for over 90% of global production, foundry coke, used for iron and steel foundry, casting on non-ferrous metals, and manufacture of insulation products like mineral wool, and heating coke, for heating purposes used as smokeless fuel. As I mentioned before, coke is an essential raw material for steel production. In this chart, we can observe that over the last several years, global coke production has doubled. The peak of production was in 2014. Currently, it's about 650 million tons of coke produced per year, and this amount is at similar level since 2015. As you probably expect, the largest coke producer is China, which produces over 400 million tons of coke annually. Other largest producers are Japan, about 30 million tons coke per year, Russia, more than 28 million tons coke per year, and India, just over 20 million tons coke per year. In the European Union, the largest producers are Poland and Germany. The production is approximately 9.5 million tons coke per year. The production of coke is closely related to the production of steel, the basic raw material necessary for the development of any economy. Steel is used in construction industry, automotive industry, household appliances, and many others. It is currently the basic construction material. Crude steel production increases year by year, and in 2018, it reached the level of approximately 1.8 billion tons per year. And of course, as with coke, the group of the largest producers is similar. As we can say, it's China, India, and Japan. Currently, more than 70% of steel is produced in basic oxygen furnaces, abbreviation is BOF, which use pig iron, which is produced in blast furnaces. And of course, the basic raw materials in the blast furnace, apart from pig iron, of course, is coke. The forecasts clearly show that in the next 50 years, the production of steel will increase, and the percent share of basic oxygen furnaces will gradually decrease in favor of other technologies, such as steel smelting in electric arc furnaces, AEF. But despite this, it is estimated that by 2050, about half of the steel will be produced in basic oxygen furnaces. Of course, old exhausted blast furnaces will be replaced with modern ones with a larger working volume of the chamber, with higher economic and ecological efficiency. This is the reason why coke is and will continue to be an important and strategic raw material for the development of the economy. I mean, mainly steel production. Of course, despite the tendency and the search for technologies to eliminate fossil fuel. In blast furnace technology, it will be replacement of PCI or natural gas. It's called substitute fuels by hydrogen or pulverized biochar. How is the role of coke in blast furnaces? The main role, the coke in blast furnaces play a three role. As it is a fuel, it's a thermal role. It is source of energy heat to process, to melt of iron ore. It is chemical role, act as reductant. It is source of reducing gases to iron ore reduction, and as a grid and support its physical function to allow liquid metal and slag to flow down to the lower part of the furnaces. And of course, it enables gas circulation within the working chamber of blast furnaces. On the next slide, we can observe the basic reaction taking place during the blast furnace process. The mixture of iron and iron ores, flaxes and coke is poured into the throat to the blast furnace. It gradually moves downward, where a number of chemical reactions essential for the process take place. Gases generated during the process remain in counter-current to the downward sliding column of materials. At the bottom of blast furnaces, there are hot blast nozzles. The oxygen in the air on contact with the coke generate carbon dioxide. Then the carbon dioxide on contact with the hot coke produce carbon monoxide. In the Boudoir reaction, the carbon monoxide produced in this way is the main reducing gas for the reduction of iron-bearing ores to liquid iron. Due to the difference in the density, because a part of iron, of course, there are some slag is being created during blast furnace process. The liquid iron flows to the bottom of the furnace, while the slag is on its surface from where is drained out. In modern blast furnaces, in addition to coke, alternative fuels such as pulverized coal or natural gas is used as a heat source. Moreover, modern furnaces are taller and have a greater working volume, which is related to the higher mass of the input material. Therefore, the physical role of coke is increasing in importance. That is to say, providing a grid for the columns of material and the gas permeability of the bed. For example, in this slide, we can see the consumption of coke and PCA, I mean pulverized coal injection per ton of pig iron. The higher, as we can see, the higher PCI usage, the lower the coke consumption. As is shown in the diagram, the coke consumption per ton of pig iron is over 300 kilograms per 1 ton of pig iron produced. In several previous slides, I tried to show how important coke is in the production of steel. In the following, I'll try to present the method of producing of coke in coke-making industry. The industrial production of coke is based on high temperature degassing of the coal charge without air access in the coke oven batteries. It's called pyrolysis process. Coke temperature in the middle of the charge, in the middle of the oven, is between 950 and 1000 Celsius degree. The main product of the process is coke. It's approximately between 75 and 78%, and raw coke oven gas, which is intended for further processing in a byproduct plant. For obtain cleaned gas, for battery firing, about between 40 and 55% cleaned gas is used for battery heating, and the excess gas can be sold or used for hydroelectric production. And apart of coke, we have byproducts like tar, benzol,
which contains benzene, toluene, or xylene, ammonium sulfate, or sulfur. We can generally distinguish two types of industrial coke production technology. Coke production in batteries with or without recovery of byproduct, so-called non-recovery or heat recovery batteries. Depending on the methods of loading the coal charge into the battery, each of these technologies is divided into two. Top, sometimes called gravity charged, and stamp charged technology. Moreover, as the name implies, the main difference between the two technologies is the recovery of byproduct from raw coke oven gas. In the case of byproduct coke making, the raw coke oven gas passes through the process system to recover a number of valuable chemical products. But in the case of non-recovery or heat recovery, however, gas is only used to heat the battery and produce heat or electricity. In the case of gravity charged battery, the coal blend is gravity charged into the coking chamber from the top of the battery through the charging holes located in the battery roof. In the case of stamp charged battery, the coal charge is first compacted in a steel box by a row of stampers, and in the form of stamped coal cake, it is pushed into the oven chamber through oven door, which are located on the machine side of the coke oven battery. We can observe that in both cases, we obtain different parameters of the coal charge for coking. Thanks to the stamping process, we obtain a much higher bulk density of coal cake, of coal charge, which enables the production of better quality coke or production of coke of the same quality, but with use of more weaker and cheaper coals in coking blend, sometimes even non-coking coals. But the use of stamp charge technology requires a deeper grinding and higher moisture content of the coals to ensure proper stability, mechanical strength of prepared coal cake. What is the advantage of stamp charging? As I said before, the higher bulk density of coal charge enable to produce coke with higher coke strength after reaction index, lower abrasive index. I mentioned about lower cost of coking blends, and of course, higher density is related to higher oven throughput. But about the coking quality parameters, I will say in the next slides. In the next slide, you can see a photo of gravity charged battery at one of the Polish coking plants. This battery consists of 78 individual vertical ovens with a chamber height of 5.5 meters, average chamber width 41 centimeters, and in general the length of the chamber is about 12 meters, and the size of the part of the oven is more than 100 meters. This battery production capacity is about 750,000 tons coke per year. In this photo, you can see the roof of the battery, top charged battery, the charging car at the end of the battery, and the charging holes through which the coal is loaded to the ovens. In the next photo, we can see the stamped coal cake. As we can see, the height of the cake is about 6 meters. the width of the cake is 45 centimeters, and the length of the stamped coal cake is 16 meters. On this picture, we can see stamp charged coke oven battery in the Częstochowa Nowa coking plant in Poland. The battery was commissioned a few years ago. In the foreground, we can see this so-called stamping, charging, and pushing car. Abbreviation is SCP machine or SCP car, which, as the name suggests, the role of this machine is stamping the coal charge, filling into the chamber, and pushing out the coke. Here we can see the heat recovery coke oven battery. It can be seen that the layout of the oven and the geometry of the chambers are different from byproduct coke ovens. The ovens are about 4.5 meters width, 2.5 meters height, and about 13 meters long. Here we can see the charging car and coal tower. This is the charging car and coal tower from which coal is loaded into the charging car. Here we can see the photo. There are non-heat recovery ovens under construction. So this is the internal chamber of the heat recovery coke oven. As a curiosity, I wanted to show a photo of the historic Cokedale coking plant, which is located in the USA. We can observe that the arrangement of individual ovens is very similar as the current heat recovery batteries. It's almost identical. Of course, in those times, there was no recovery of heat. It was typical non-recovery battery. All evolving gas from the coke charge was going to the stack. So there was no recover any heat or any energy. This coking plant operated in the first half of 20th century and produced about 800 tons of coke per day. As a rule, non-recovery batteries are arranged horizontally, but they also exist vertically. This is the example of vertical type heat recovery coke oven battery located in China. This diagram shows the basic difference between the byproduct oven and the heat recovery oven. Apart from the aforementioned differences in the geometry of the chambers, the main difference is the method of heat transfer to the coal charge. In case of byproduct ovens, heat is transferred to the load charge to the coking blend indirectly through the ceramic walls between the heating flues, whereas coke oven gas combusted. The waste gas have no contact with the coal charge. Due to relatively low width of the charge, the coking process time is usually between 16 and 23 hours, and the escaping of coke oven gas is discharged from the chamber directly to the collecting main. For heat recovery ovens, by the right side, we have hybrid heat transfer case. The raw coke oven gas released from coal blend, which is located in the coke oven chamber, is burned directly above the coal charge with an, of course, insufficient amount of air. Air is entered to the chamber through the holes in the chamber door. The hydraulic system of the battery operates under, of course, negative pressure, which allows to suck the air and eliminate emission from the oven. The partially burned gas is going through downcomers to the bottom flues. Here, the secondary air is supplied to these channels and combustion of the gases also take place. In this case, the heat is indirectly transmitted through the floor, through the sole of the oven to the cold charge. Of course, the waste gas then goes to steam boiler to be used to produce steam, which is used in steam turbine coupled with electric generator to produce electric energy. In this case, because of cold bed of between 1 and 1.2 height, it's more than doubled than width of the classical byproduct oven. The cooking time in such ovens can be up to even 38 hours, 48 hours. On the next slide, we can see a diagram of the classic byproduct technology. Cooking coals from the storage are transported to the preparation plant, where are subjected to a number of operations such as crushing, blending, sometimes screening, or moisture addition. Of course, depending on the grinding technology, the coals may also be screened to see the specific grain fraction. As a rule, single coals are ground and then mixed to homogenize the coal blend. For crushing operation, in general, the hammer mills are used. The prepared coal blend is directed to the coal tower, from where it is loaded into the oven chambers through the charging car, as we could see in the previous slides. In the battery, the coal blend is carbonized for a period of between 16 and 23 hours. After the process, the coke is pushed from the battery to quenching car and sent to wet quenching or dry quenching process. Of course, wet quenching process involves spraying coke with water with a special quenching tower, and then the cooled coke is transported to the wharf and then to the sorting plant. Dry quenching facilities consist in cooling the coke by passing inert gas through the coke bed. The gas extracts heat from the coke and transfer it to the water in the steam boiler. Of course, the gas is in the closed circuit. The coke oven gas released during the process is sucked from the battery to the collecting main. Just before collecting main, raw gas is cooled down from above 815 degree to about 80 degree by water spraying, and condensed tar is separated in gas liquid separator. The negative pressure necessary for gas suction from the battery is generated by exhausters. In the next step, the gas is cooled in primary coolers, which is heat exchanger with water, with use of water. And then the residual tar is removed with the electrostatic tar precipitator. Cooled and pretreated gas is directed to individual processing nodes for removing ammonia, benzyl, and desulfurization. Then is directed to the final cooling. As I said before, about half of the gas is returned to the process to heat the coke oven battery. The rest of gas can be sold or used to produce heat or electricity, or in different technologies to produce valuable chemicals, for example, methanol. A part of coke oven gas, the resulting tar can also be distilled to obtain valuable chemical products like light oils, carbolic oil, naphthalene oil, wash oil, anthracene oil, or pitch. In general, the technology of cold preparation in heat recovery coke making is similar to that for byproduct coke making. The only difference is, apart from coke, the coke oven battery produces waste gases. Waste gases are used in steam boiler. The generated steam is directed to the turbine is connected to the electricity generator, and the resulting electricity feeds the power grid. From which raw materials we can produce the coke? In relation to coking process, coals can be classified into two categories: non-coking coals and coking coals. As I mentioned before, coking coals are the bituminous coals with an average qualification degree, and it passes through the plastic state during its heating without air access. Volatile matter in such coals is about 16 to 35%. Many parameters, as you can see, can be evaluated to assess the suitability of coal for the coking process. And of course, based on the knowledge of these parameters, recipes of coke blend are established. The most popular, commonly assessed parameters is, of course, the parameters of proximate analysis. I mean moisture content, ash content, volatile matter content, fixed carbon, the ash chemical composition, the composition of oxide in the ash, because some oxide can act as the catalyst of carbon dioxide reaction, gasification of coke. Very important things is petrographic analysis, because coals contain macerals and like vitranite, inertinite, or liptinite, and different kinds of macerals act in different way during pyrolysis process. And of course, from the coking process, very important parameters are so-called coking or caking properties, like free swelling index, Giseler fluidity, Roga index, Sapochnikov plastometry, Arnould-Audibert dilatometry, Gray-King coke type, or coking pressure, which can be determined in movable wall oven. It's very useful parameter which can help assess the safety of coking process in aspect of coke oven battery, because there are some coals which can generate excessive pressure and which can damage the oven walls of the coke oven battery. So it's also important to assess the coking pressure of the coking coals. The free swelling index sometimes is defined as crucible swelling number. The abbreviation is CSN. This is a measure of the increase in volume of the coal when it's heated in a small crucible in the absence of air. The Roga index can provide information of the caking properties of the coal. In general, it evaluates the cohesion of resulting coke in a drum tumbler when coal is mixed with a fixed amount of a specific anthracite, which acts as inert agent. And of course, this blend is subjected to rapid heating rate up to 850 degrees. And after, there is subjected to drum tumbler. Very important parameters is Giseler plastometer and Audibert-Arnould dilatometer test. This test in general monitor how the coal behaves as the different macerals melt, devolatilize, and resolidify at different temperature during the carbonization process. The Gieseler plastometer evaluates the coal behavior by measuring the fluidity of a packet coal powder at it is heat, whereas the Arno-Audibert dilatometry measure the contraction and expansion of the powdered sample pressed into a cylindrical coal pencil. These properties are important to classify coals and of great relevance when different coals are to be blended for coke production, to of course ensure compatibility of the different blend components. Greiking coke type, this is the test which can determine the coking properties. It's a simple coking test. Finally, crushed coal is heated in a glass retort, and then the shape, texture, and appearance of the obtained coke is compared to the standards to give a letter, which is the Greiking coke type. Of course, the letter values from A, which mean non-coking coals, to G, and after G we have G1 to G9, which indicate superior coking properties. Sapochnikov test was developed by Russian researchers, and we can use the plastic layer thickness of coking coal and contraction indices. In general, coal blending procedure for coke production are based on combination of rheologic and petrographic parameters for individual coal samples, which can be used for select coals to make up a blend with specific coking properties. Currently, the basic parameters in assessing the quality of coke are Micum indices and Nippon Steel Corporation indices, such as carbon coke reactivity index CRI and coke strength after reaction CSR. Moreover, significant parameters for the processes of using coke are the granulation, sieve analysis, proximate analysis like ash, moisture, and volatiles, ultimate analysis, carbon, hydrogen, nitrogen, sulfur, oxygen, chlorine, phosphorus, or mercury content, and as mentioned before, ash chemical analysis, because some of the ash oxides or some of the minerals have catalytic action on reaction of gasification of coke by carbon dioxide. So they can increase the reactivity of produced coke, which is not favored in aspect of blast furnace processes, because in general, higher the reactivity of coke, lower the carbon coke strength after reaction. The principle of determination of Micum or IRSID parameters based on mechanical treatment of coke sample with a specific in a rotating drum, and then assessing the mechanical strength. When we talk about Micum, the test is equals 100 rotation. In case of IRSID test, there is 500 rotation of drums. And the most frequently rated parameters is abrasive index M10, which reflect the share of the test sample with a diameter of less than 10 millimeters after drumming. And the mechanical strength, it can be M40 or M80. It reflects the share of the test sample with a diameter greater than greater than 40 or 80 millimeters after revolution of the drum. In general, in aspect of blast furnace process, it is better to have a relatively low abrasive index and a relatively high mechanical strength. The second important parameters, currently probably the most important coke quality parameters, commonly assessed in the whole world, are Nippon Steel Corporation parameters, such as coke reactivity index, CRI, and coke strength after reaction. On this photo, we can see the facilities to assess these coke quality parameters produced in our institute. The principle of the method is to gasify a 200 gram of coke with the proper grain size between 19 and 22.4 millimeters in the atmosphere of carbon dioxide at the temperature or 1100 Celsius degree. The duration of process is exactly 2 hours. The coke reactivity index CRI is calculated from the amount of weight loss, and then the coke sample after gasification is mechanically processed in a rotary drum under the specific condition, 600 revolution with 12 revolution per minute. And then the weight of grain with dimension above 10 millimeters is determined to determine the CSR index. Of course, for different blast furnaces, there are different requirements for blast furnace coke. As we can see, the higher the volume of the working chamber of the blast furnaces, the better quality the coke should be. We can see the CRI should be lower, CSR should be higher. As I mentioned before, because when we have higher working volume of blast furnace, there is higher mass of the iron bearing and in general the feed to the blast furnace. So coke is to be more strengther. It should be with higher mechanical strength to ensure the proper permeability of the feed. And of course, it shouldn't be degraded. When we have a higher reactivity and lower coke strength after reaction, the coke is diminished too fast, and of course the operation of the blast furnaces effectivity is decreased. Here we have factor influencing coke quality. As I mentioned before, the main determinant of coke quality is the quality of coking coals. I mean qualification degree, coking properties, petrology, mineralogy. The second factors are coal blend preparation. I think the most important in coal blend preparation is bulk density, because in general, higher the bulk density, better the coke quality. But also the other factors are important, like granulation of coal and of course moisture content, because both crushing fineness and moisture content also influence on bulk density, so it directly affects the coke quality. Very important are coking process conditions like coking time, oven width, heating wall temperature, final coke temperature in the middle, and soaking time. The last but not least, the coke treatment is also important, because stabilization of coke on the, conveyor belts during technological system of the coke oven battery also influence the mechanical strength of coke. And also quenching of coke play some role, because we can imagine when we spray the hot coke with the temperature of 1000 Celsius degree by cold water, there are some tension in the material and some fissuring can occur. So it influences negatively of mechanical strength of coke. But in the case of dry quenching, we can also extract the waste heat, which is loose in the case of wet quenching of coke. And of course, the gases are more, more delicate for coke structure, so they can influence a bit positively on coke quality parameters. And we are going to the conclusion. Coke is essential raw material for steel making process. Blast furnace process will be leading process in pig iron production within the next 30 years. The development of blast furnace technology will force the necessity to increase the economic quality and environmental effectiveness of coke production. And of course, in order to reduce carbon dioxide emission to the environment, in coke-making technologies will be developed some methods for producing biocoke, the production of coke based on coal and biomass blend, and in the case of blast furnace technology, some replacement of substitute fuels with fossil origin, like natural gas or pulverized coal injection. This replacement, it will be by renewable fuels such as hydrogen or biochar. I mean pulverized, thermally treated biomass. Thank you very much for your attention. If you have any question, please please ask. If I can answer, I will try to answer. Or if you have any more detailed question, please send me an email. I will try to answer. And of course, in behalf of Institute for Chemical Processing of Coal, I would like once again thank for the possibility of make presentation. And of course, I would like to welcome you to cooperation in some international project related to fuels processing. Thank you very much.
You're welcome, Mr. Misal, and I also I'm happy to see you with us this afternoon in this Zoom meeting. And honestly, I'm also hope that in the future we can have a cooperation between the two institutions, because here in our campus there are several iron and steel industry. For example, Krakatau Steel, Krakatau Nippon Steel, POSCO, and etc. So we have a possible option to have a collaboration.
I know these companies in general. The world is very, very small now. We can cooperate in different way. We have in our institute all the facilities necessary to assess the not only for coke, for different fuels quality. And of course, I can send the email with internet link to our website. There are many very interesting things. And of course, we are open to cooperation. I know that Indonesia are very intensive, are in very intensive development of steel making processes and coke making processes. So it is good sign to make some cooperation in the future, because we have in Poland in general, we have more than 100 years of operation in coke oven batteries. So we obtained some, how to say, experience about that. So we would like to join the knowledge transfer technology. So we are open to cooperation. So thank you very much for the opportunity to make presentation.
Okay, so maybe is there any question for Mr. Misal? Or how to pronounce your name? Misal Rejdak?
Rejdak, Michał Rejdak.
Michał Rejdak.
Or Michael. Some people English language say Michael, because it's Michał, it's Michael in English.
So for the participant, do you want to ask a question to Mr. Michał? So
yes, Pak Adit. Mohon izin, Pak.
Okay. Mr. Yantagor.
Ya. Halo, Mr. Michał.
Hello.
I am curious about two things, and I have two questions for you. The first is it possible to use coke oven gas for reduction gas, for reduction processes for iron? Is it possible to use the coke oven gas? And then the second question is, if the coke produced have a bad CRI and CSR, let's say not so good quality, is it given from the raw material, from the coal, or can we do something about it in the coke making process? That's all. Thank you.
Okay, I try to answer for the first question. In general, in Poland, we do not use the coke oven gas for reduction, but maybe not for reduction, because there are small amount of possible, maybe not possible for reduction of. There are many amount of hydrogen in coke oven gas, so so we can imagine that hydrogen in coke oven gas can be used for reduction of iron ore, but in general, in blast furnace, the main reducing gas is carbon monoxide. So I mean the coke oven gas, it should be rather used, for example, like as substitute fuels to supply heat, rather than like reducing agent. But it's my opinion. In Poland, we do not use the coke oven gas like reducing agent, because in my opinion there are many more efficient way to use coke oven gas. For example, of course, the half of gas produced is being used for firing of the battery, and the half we can use for electricity generation, for make steam in steam boiler and coupling with the steam turbine and generate electricity, or producing more valuable chemicals like methanol. This is I try to answer for the first question, but I have. Could you repeat the second question, because I did not understood well. I did understand well because probably of quality of the sound.
Yeah, okay. The second question is about the CRI then and CSR.
Yes.
The quality of the coke. If the CRI and the CSR is not good, can we do something about it in the process, in the coke making process, or is it just given by the quality of the raw material, the coal?
Yes. In general, when we have to proper use of coke in blast furnaces, we have the proper quality of coke related to our technical condition of the blast furnaces. In general, we shouldn't put the coke with lower quality to our blast furnaces. And what we can do, to increase the parameters like CRI or CSR, we can implement some other technology. Of course, as you said before, the main factor which determine these parameters are the coal, but it are also coal preparation processes and cooking condition. But when we have coke oven battery, we have some coal, some cooking blends. We have to prepare. We have to buy just better coals to have a better coke. But we can also enhance the CSR and in general quality parameters by implement of different technologies. For example, like coal moisture control. I mean the preheating of coal charge, for example, from 10% of moisture to 5% of moisture. The preheating of coal charge will enhance the bulk density of coal blend, and thus we can obtain the coke with better quality parameters. We can use some partial briquetting of coal charge. This is the same way we can increase the bulk density of the coal charge, and then the CSR parameters could be a few percentage point higher. And of course, currently, the better way to produce coke is use the stump charging technology. So this is the possible action to increase the coke quality. But of course, at the beginning is the coal quality. If we have bad, colloquially said, bad coal, we will not have a good coke. And of course, the mineralogy of coal used is very important, because when we have too much ash or mineral matter in the coals, of course, it also have detrimental effect of coke quality. And the ash composition also play important role, because there are some parameters called alkalinity index. This is the ratio between some oxides content in the ash, and if we have alkalinity index higher, of course, it also have detrimental effect of coke quality, because this oxide have catalytic effect of carbon dioxide reaction, and thus the reactivity is higher and the coke strength after reaction is lower. So we need to our focus on coal quality, and after we have some method to increase the coal quality and the coke oven batteries. I hope I try to explain your question.
Yeah, it's very clear. Thank you, sir.
Thank you.
Thank you, Mr. Yantagor. So I just curious, what company that use the coal product of your company? Is it only for domestic use, or the coal export maybe to any other country, for example?
In general, for coke production in Poland, we use most of our domestic coals, but a part of domestic coals in Polish coking plants, there are also coals from import from different countries like USA, Australia, Mozambique, and many different countries. But our coking coal are also exported to the other countries, to the European Union countries and other countries. So in general, in our domestic production, we use our coal and coal from import. Coals from import.
Okay. I think we have a question from Mrs. Erlina Yustanti.
Yeah, thank you. Dr. Michal Reda, I'm very lucky hear your nice and very interesting result from your study. You successfully produced fuel bucket from blending cooking with biomass. I read your nice publication through Multidiscipline Publisher Institute and Mineral Engineering Conference on December last year. I have 3 questions for you, sir. First, you mentioned that coke treatment like sprayer water on hot coke can increase cooking strength. Can you help me understand this mechanism? And then question 2, why fluidity are very important on blending? And the last, what do you think if the ash content and volatile matter are high, will it produce high calories? Commonly, biocoke must have minimum 6,500 calories each gram. Thank you, sir.
Okay, I'll try to answer all of the question. Probably within the first question, there was some misunderstanding. I said that spraying, I mean wet quenching of coke have a bit detrimental effect of coke quality, because when the hot coke is in contact with cold water, there is some tension between internal particles of coke, so it has detrimental effect of coke quality. Moreover, the vapor of water penetrating inside the pores of coke, in a bit way, how to say, developing the surface area, and as it well known, the higher surface area is also related with higher reactivity. So wet quenching coke definitely not increase the quality parameters, but decrease quality parameters. Of course, it's not totally decrease. It's about when we use dry quenching coke, for example, we can increase CSR index by two, maybe more or less 2 CSR. So when we use dry quenching, so this is that difference. Second, I don't exactly understand the second question. Could you repeat, please? Because of course the
second question: why fluidity are very important on blending?
Why? Which parameter?
Fluidity.
Fluidity. Okay, because fluidity is very important because when the coal is being transformed into coke, or other way, the coal contains so-called basic structural units. It's 2 or 3 polyaromatic layers, and this is the basic structural unit of coals. And these structural units are in coals are linked in different way, by cross-linkings in aliphatic chains and something like this. And during the pyrolysis process, these cross-linkings are breaking, and this in the range of between 350 degrees and 500, the coal becomes fluid, and this fluid allow these basic structural units to rearrangement and create an isotropic texture of coke. Of course, if the fluidity is too low, there is small potential to rearrangement of coke texture. And if fluidity is too high, is also not good, because if we have too high fluidity, we have high permeable coal plastic layer, which generates very high porosity of coke. So according to literature reports, the adequate, the optimal fluidity of the blend, it's between 100, 200 and maximum 800 or 1000. So because when we have very big, very high fluidity values, like for some American coal, there are some even 30, 40, 50,000% of DDPM by Giseler. The coke produced from that coals are very porosity, like sponge, very, and the layer of how to say, the pore thickness, pore wall are very small, so the strength of the coke is also decreased. So conclusion, the fluidity of the blend enable to rearrangement of basic structural units from contained in coal to coke, because they can enable to create a texture of coke. Okay.
Okay, the last question, sir.
Yes, the last question I have also. Could you repeat the last question?
Oh, okay. The last question. What do you think? If the S content and volatilometer are high, will it produce high calorie too?
High calorie, do you mean calorific value of coke?
Yes.
Of course, ash, I mean mineral matter, decrease the calorific value of coke, but in general, the calorific value of coke, the volatiles. You know, you mean volatiles in coal or in coke? Because the coke is almost without volatiles. The amount of volatiles in coke is about 0.5% or 1%. This is the value. You mean volatiles in coal or in coke?
In coal.
Yes. Okay. It's
okay. Thank you, sir.
Depends on volatiles. during the cooking process, almost whole of volatiles are evolved. So in general, when the coke process is completed, it's no matter when we start 28 volatiles or 22 volatiles in cooking blend. In coke, at the end, we have almost the same level of volatiles. So I think in general, it should be a big influence. Volatiles in coke shouldn't have big influence of calorific value of coke. And of course, ash have value, because ash, I mean mineral matters, remain mainly the very big, most of mineral matters remain in the coke. So the higher the ash content, lower the calorific value of the coke.
Thank you, sir.
Thank you, Ms. Erlina. So, do we still have a question for Mr. Michal? So I think we don't have any question anymore.
Well, thank you very much for seminar.
Yes.
Nice to meet you.
Yeah, nice to meet you too. And thank you for all participants, Mrs. Erlina, Mr. Yantagor, and etc. And so also Dr. Albertus, I think, and all the participants. I would like to thank you. Also to Dr. Michal Redak. I think.
Yes, okay.
So thank you very much. I hope, yeah, for example, Mrs. Erlina, she research. I think it's about coke making technologies and materials. So as a head of department, I will give support to Mrs. Erlina to have a collaboration to with you in the future. So once again, thank you very much, and I close this online seminar for today, and goodbye everybody, and see you on next week, for example, on Monday, because every Monday we have this online seminar. So thank you very much, and bye.
Bye. Thank you.
Ya, terima kasih Pak. Thank you.
Bye.